Okay, so today we're going to be looking at infinite geometric series. Okay, so looking at infinite geometric series. So last time we looked at how to work out the values or using geometric series. We also looked at how to sum a geometric series up to a certain term. But today we're going to be looking at, does a geometric series go on for infinite, or would it eventually sum to an actual value of number? Okay, so let's consider the geometric series the following. Okay, so let's consider this. Let's consider the geometric series. One, 2, 4, 8, and so on. Okay, so our first term being the value a is 1, and we can see quite quickly here that every term is getting doubled after that, so the ratio that we're multiplying each number by to get the next term is 2. So if I was to put in the sum of that formula, okay, so again using your formula sheet, up to say to the n terms, what that would look like is a bracket 1 minus r to the power n over 1 minus r. Okay, so that's the formula we've got. Putting in our values, well, a is 1, so it's 1 minus 2 to the power n, which equals 1 divided by 1 minus 2. So we'll have 1 minus 2 to the power n divided by negative 1, which means that it becomes 2 to the power n minus 1. So no matter what term we would want to sum this up to, that's what that geometric series, we could evaluate it if we knew the number of terms. So an example being, if n was 5, so if we only wanted to go up to the fifth term, then the sum of the fifth term, if you put n equals 5 into that expression, then you would get the value 31. But if I made n equals 10, I want to sum the first 10 terms of that geometric series, so putting 10 into that expression there, I would get 1023. So you can see there's a massive difference in the summation totals there, even just going up another 5 terms. And if I went up even further, so let's say I went up to the 20th term, which means I'm putting n equals 20 into there, then the value of that sum would become 1,048,575. So you can see it didn't take very long, it didn't take that many terms for that summation of that series to go past 1 million. Okay, it only took up to the first 20 terms basically, okay? Or we know in the 20th term that would be the case. So you can see that every time we would want to do it for more terms with a geometric series like this, the value is increasing. Okay, so the value of Sn is increasing without limit. And the series does not have a sum to infinity. Okay, so you can quickly see that if I kept going up the terms and somehow it's just going to go on and on and on, as the numbers just going to get bigger and bigger and bigger. Okay, that's why there's no limit to it. Okay, it would just keep going all the way. It would sum to infinity basically. Okay, at a certain point it's just going to get too big, it'd be infinity. Okay, let's now consider another geometric series. So geometric series one, half, quarter, an eighth, and so on. Okay, so here's just another geometric series. let's see what would happen if we try to work out an expression for the summation of this. So we can see here that A would equal 1, so that's our first term again. However, the ratio would be a half. Yeah, we're halving every term to get the next term here, so R would be the value of half. So putting that into the formula, then S of n, so it's A bracket 1 minus R to the power n over 1 minus R. Then A is 1, so that just stays as 1, so that's going to be 1 minus a half to the power n. One minus a half. Okay. Which would be 1 minus 1 half to the power n. 1 minus a half is a half there. And I can just tidy that up, multiply both numerator and denominator by 2. That'll give me an expression of 2 bracket 1 minus a half to the power n. Okay, so again, I found an expression so that if I were to sum the first n terms, I would just substitute the value n into that expression there to give me what that would be. So again, we'll do the same things, we'll keep the same numbers that we done last time. So when n was 5, if I put that into this geometric series, so the sum of 5, putting n as 5 into that would give me a value of 1.9375 ... Okay. If I made n equals 10, so the sum of the first 10 terms, put the value 10 into that expression, you'd get 1.9980. Continued. And if I do 20, then the sum of the 20 first terms of that sequence would be 1.9999. Continued. Okay, and you can see that's a totally different thing that's happened this time round to the last term. Okay, these numbers aren't getting much away from each other the more terms used. In fact, we're actually getting closer to what it actually goes down to. Okay, so what we can see here is that the value, the more terms you add, it's getting closer and closer to the value 2 here, isn't it? Okay, that is, even at the 20 terms, that is very, 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 very close to the value 2. So the value of Sn is approaching a limit of 2. Okay, which means that this series has a sum to infinity equal to 2. So if we summed the first almost infinite amount of terms in this sequence, it would still approach a value of 2. Okay, how we can write that? Okay, so written as, so if I were to sum the first infinite terms, it would just give me a value 2. Okay, that's what the sum goes to, a limit of 2. So there is a reason why that happened in the second case and not the first case. Okay, it's very similar to the recurrence relations from higher regard when you looked at limits last year. Okay, so in general, whether or not a geometric series will have a sum to infinity depends only on the value of R. Okay, a ratio. Okay, that's what it depends on. Okay, so a geometric series will have a sum to infinity if r is between -1 and 1. Okay. Notice how I'm not saying that it has to be less than or equal to, okay, or greater than or equal to. It has to be between -1 and 1. Okay, because if it's a value 1, for example, that's your what you're multiplying everything by, it would just stay the same. So you're summing up at n times basically. Okay. Whereas if it's less than 1 or if it's greater than -1 but less than 1, then the numbers do go into a limit, okay, as you sum them up. Okay. And the reason being, so if we do have -1, it's between -1 and 1, then what that means that if we put r to the power n, okay, we make n a large term, a large number, okay, then it goes towards 0, okay. So for example, if you have like a half as your r, and you do it to the power, say 30, or it does go towards 0, okay, it gets really small the more times you do it, okay. So as n goes to infinity. So as n gets larger, the value of r to the power n goes towards 0 if it's between -1 and 1. And what that means is the sum. So again, the sum would be, well, it's normally a to the bracket 1 minus r to the power n, but if r to the n goes to the 0, then it's 1 minus 0 there. And we have 1 minus r on the bottom. Notice that wouldn't disappear because that's just r to the power 1, okay? So that would still be a value, okay? It wouldn't go towards 0 or anything like that. Therefore, that would just be a or 1 minus r, okay? So I know that's a lot of information there, but in summary, if r is between -1 and 1, then the sum to infinity is your a value divided by 1 over r. Okay, you would be able to work out that value there. Okay, so that is the rule there. Okay, what we'll do is we'll look at a couple of examples to show you how these questions can work. Okay. So, example 1. So find the sum to infinity of the geometric series (250, 150, 90, 54, and so on. Okay. So here, solution, sorry. First term A is 250, we can see that. We don't know what the ratio is, it's maybe a bit harder to spot. What you do is you divide consecutive terms to get that. So if we take the second term, for example, which is 150, we'll divide that by 250. Okay, that would work out what the ratio was that took me from the first term to the second term. Simplify that down. 3/5. Okay, so r is a value 3 over 5. Therefore, and this is what you need to write down. Okay, like the current relations, since r is in that category, it's between -1 and 1. So a sum to infinity exists. Therefore, to work it out, the sum to infinity, well, I've got a new rule, which is a over 1 minus r. A was 250. 1 take away, r was 3/5. Okay. So that's 250 divided by 2/5, which would give you an answer of 625. Okay. So that's what that series, if you summed up all the values in it, okay, up to infinite values, that's what the sum would tend to go towards, okay? It would tend to 625 as a limit, okay? So that's just a first example there of just using the new rule and working out A and R to get you that sum to infinity. Okay with that one? Okay, look at one more, then I'll get you to practice some of these. So example 2. So again, a bit different, okay? So a geometric series has first term 28, and sum to infinity (16). Find the fourth term in the sequence. Okay, so you can see it's a bit of a different type of question we need to try and work out here. We've been told the first term in this series is 28. We know it's geometric, and we know that it does have a sum to infinity of 16, which means r is between -1 and 1. But we need to work out what the fourth term in the sequence would have been. Okay, so let's look at the solution. So we know that our first term is 28, therefore A is the value 28, that's fine. Okay. Now I know it did have a sum to infinity, which we work normally out by A over 1 minus R. And I know that has to equal 16. Okay, so that's what I had to try and work out there. Putting in my values of A, so that's going to be 28 over 1 minus R equals 16. Okay. Therefore, if I bring the 1 minus R and multiply it, it's going to be 28 equals 16 lots of 1 minus R. Okay, so that's 28 equals 16 minus 16R. Taking off the 16 on both sides, so that's going to be 12 equals negative 16R, which therefore tells me that R would be negative 3 over 4. Okay, which is good because I did expect to get an answer between -1 and 1, didn't I? Because it did tell me I had a series. So that is a positive, not positive, it's negative actually, but that is actually what I was hoping to try and achieve there. Okay, if I got something greater than less than -1 or greater than 1, I would have felt I'd done something wrong there. Okay, so now I can use that information. So I wanted to find the fourth term. In a geometric series, how you work at the fourth term is a r to the power n minus 1, so 4 minus 1 is 3, so it's to the power 3. So a was 28, that's going to have to multiply -3 over 4 cubed, which would give me an answer -11 and 13/16. Okay, and that's how I could work out the fourth term there. Okay with that?